Hello? Hello?
Prova, prova.
Hello?
Hello, Wendy.
Hello?
Yes, good. We are all here in Pescara, and
Okay.
there are many people
Okay.
ready to listen to you. They are from all over the world. In the first line, you see Rashid Sunyaev. Then you see Dili, who will receive a prize tomorrow, and Grant Matthews, and so many people from all over the world. We have, in principle, 700 people participating, but you know, we have been working since this morning, and we are at the end of plenary lecture of this morning, and then we had various parallel sessions, 10 parallel sessions in the afternoon. And now we are left with, I presume, 100 people which have resisted from 700 this morning, who have resisted all the way to now to listen to your word. We thank you very much for accepting our invitation, and we look forward to your presentation. And hope very much that the next time you come in Pescara, because we are next to the beach in a place very nice with a lot of pine tree, and the university is nearby, and we are having a great time, as you will see from the program. We look forward to your presentation. You have any question?
No, I'm glad to see you here. And I'm talking to you from Pasadena, California. So it's morning for me, and I'm grateful that people are, after such a long day, willing to attend another talk. As I understand it, this is a public lecture, so I'm
Yes,
here in the
yes.
public audience. And I'm pleased to join you. I was in Rome just a couple weeks ago, so and I had another meeting in conflict, not able to join you in person, but I'm glad that I can join you this way. So
Rashid
what else?
had a comment. Rashid, what you said?
Public lecture for scientists.
Ah, yes, public lecture for scientists, because they are all relativistic astrophysics, and we are having a tremendous excitement, because there are many points. Tomorrow we will have the presentation of the Grossman Award to Dili and Vicky Caspi. And in the evening, we will have the Grossman Award to the people in Los Alamos who have made all the work with us on the simulation of the gamma ray burst. And we have a very, very exciting moment because after 50 years, I remember we introduced the gamma ray burst in a famous meeting of the AAAS in San Francisco, maybe 52 years ago. But only these days, the last days, we understood what the gamma ray burst looks like. There are 7 different episodes. It's very, very exciting. And we think that is.
Uh-oh. I've lost sound. I don't know if you can hear me, but I no longer hear you. Hmm.
Hello, can you hear
Oh,
me?
yes, I hear you
Okay.
again.
And
Good.
we have a very exciting time because I think we have even understood how the supernova 1054 was generated by a gamma ray burst. But we will send you the publication. We listen now to you and please proceed. We can hear you beautifully.
Okay, good. As I said, so I understood I'm giving a public talk. I will take Rashid's comments to heart, and I will dwell a little less on history, which I assume is familiar to this audience, and dwell a little more on the science end of things, and happy, of course, to answer questions at the end. So I will try and share my screen now, and let's see. Um, Um, so do you see my screen now? Are you able to see my screen? Uh-oh, I've lost your sound again, I think. I don't know if you can hear me. Hmm. Are you able to hear me?
Hello, yes,
Oh,
we
okay.
are hearing you beautifully.
Okay, good. Now
We
I hear
have
you.
just a small problem with the microphone, but otherwise we see this beautiful picture of space, telescope in the mountains and so forth and so on.
Super. Okay, I will proceed then, and maybe if there's a problem, you can let me know. So it's a pleasure again to be speaking with you, and it's an exciting time in cosmology right now. And as we know, in the last couple of decades, there's been enormous both discoveries and changes in our overall perception and what we now consider to be the standard model of cosmology. And there's been a very healthy interface between theory and observations. I will talk at the observational end of things today. And as we're all familiar, the discovery of the expansion of the universe in the 1920s up through the characterization of the composition of the universe with the dark matter and dark energy components, and most recently with the possibility that our current standard model, which of course is a lambda CDM model, cold dark matter plus dark energy, are there gaps in that? Is there a possibility that there's fundamental missing physics? And that's what we're trying to address now, and most recently with the James Webb Space Telescope. And I will touch on that briefly also. Now this is interesting. What I usually advance with. Okay, I can advance here. So most of what I will talk about today are recent observational results. And just to give you a sense of where I spend a lot of my time in the Andes Mountains in Chile. And this is the console of the Magellan telescope, a 6.5 meter telescope in Chile, where we've done a lot of the calibration work necessary for the extragalactic distance scale. So you might wonder why I take myself into the Andes Mountains that at certain times of the year, are crawling with tarantulas and scorpions. And fortunately, they don't usually come onto the keyboard, but they are a presence on the mountain. So the big progress in terms of observational astronomy has really come with the development both of detectors, charge coupled devices and infrared arrays, as well as telescopes in remote locations. Remote, of course, because we want to get away from city lights. The prevailing winds here, this is Las Campanas in the Andes Mountains in Chile, where I was sitting in the console room. And the prevailing winds come off the ocean, the Pacific Ocean, and they don't hit another mountain range until they get to Las Campanas. So there's not a lot of extra turbulence in the air, and that helps us achieve better seeing. So these dark sites are where we now are building our large telescopes. Of course, with the development of the Hubble Space Telescope, the launch of Hubble Space Telescope in 1990, where we could get above the Earth's atmosphere for the first time with almost an order of magnitude better point spread function or resolution than we had from the ground. We are now in the planning stages of very large telescopes. This is the Giant Magellan Telescope project, which is an international project that involves a number of US institutions, as well as Australia, South Korea, Brazil, the Weizmann Institute, and most recently Taiwan. And it's a 20-meter telescope, 25-meter telescope, again, to be located at Las Campanas in Chile, completed in the early 2030s. And then most recently, in terms of the context of this talk, is the launch of the James Webb Space Telescope, which has about 4 times the resolution of Hubble at the near infrared wavelengths where we're observing, and 10 times the sensitivity. So enormous jump, and comparable to what we got with Hubble over the ground in the 1990s. Now, just going back very briefly into a bit of the history and the development of telescopes in the US, much of it due to the energy and creativity and drive of George Ellery Hale, who began with the building of the Yerkes 40-inch refracting telescope in Wisconsin. Then he moved out with his family to Pasadena, where he successively built the world's largest telescopes at the time. The 60-inch telescope at Mount Wilson. This is where Harlow Shapley made the discovery that the sun is not the center of the universe, but that it's displaced and that we are located about 2/3 of the way out in a disk in the Milky Way of our galaxy. The 100-inch, where Edwin Hubble made his measurements and discovery eventually that there are other galaxies, and that overall the universe is expanding. And then, of course, the Palomar 200-inch. So a long history of telescopes in Pasadena. Now, this is the discovery plate that Edwin Hubble marked himself. You can see he was very excited when he discovered this variable. And at first he thought it was a nova. This turned out to be the discovery of a Cepheid variable in the Andromeda galaxy just over 100 years ago. So you can see this is the 6th of October, 1923. And subsequently, he measured the distances to a number of galaxies. Some of these were used by Georges Lemaitre, which now the discovery of the expansion bears both of their names, the Hubble-Lemaitre law. And he was the first person to actually marry the theory allowing for an expanding universe with the observations, and to realize the implications of Hubble's measurements. Now, Hubble in 1929 then published, well, first in the 1920s, he was able to establish that there were other galaxies beyond the Milky Way and resolve the debate that at the time people were concerned about whether or not these nebulae that had been seen on photographic plates were regions in the Milky Way where gas and dust were collapsing to form new stars, or whether they were so-called island universes in their own right and at greater distances. And it was the discovery of Cepheid variables that allowed Hubble to unambiguously show that these objects were in fact extragalactic and that they were galaxies in their own right. And this is Hubble's original plot. Velocity got the units wrong as a function of distance, and there's a considerable amount of scatter, but that correlation has held up over time. And with the development by Einstein of general relativity, which Lemaitre had allowed for the expanding solution, has led to the picture of a Big Bang universe, which was confirmed in the mid-60s with the discovery of the cosmic microwave background. And the measurement of the Hubble constant has turned out to be much more difficult in practice than Hubble or anyone at the time realized for a number of reasons. Different kinds of systematics. First of all, the photographic plates that Hubble used are notorious. They saturate at high light levels. They're nonlinear at low light levels. The plates are sensitive to blue radiation, blue wavelengths, and that's where the effects of dust, you can see the dust lanes here in Andromeda, the white, this is a negative image. Hubble was not able to correct for dust. It was not possible to do that with any reliability until we got charge-coupled devices and the capability to move into the near-infrared part of the spectrum. And then, of course, because of the resolution, there were very few objects that could be observed from the ground, from the Earth, and it wasn't until the Hubble Space Telescope that we could get above the atmosphere, increase the numbers of calibrating galaxies with Cepheids to improve these measurements. That took a long time. And just to refresh people's memories of the period luminosity relation that we have used, that has become the gold standard in measurement of distances to galaxies, which was discovered by Henrietta Swan Leavitt. And she was working in the Large and Small Magellanic Clouds and discovered that there was a correlation between the luminosity of a Cepheid and its period. It's interesting, the New York Times just published an obituary for Henrietta Leavitt in March of this year. They're going back and they have decided to acknowledge that there were contributions by women 100 years ago, but there were no obituaries done for women at that time. And really, this relationship has been the bedrock of observational cosmology. It is the foundation of Hubble's discovery. It's the foundation of what we used for the Hubble Key Project and what we still use today for measurement of the distance scale. Now, for this audience, I don't need to say the Hubble constant is important for many reasons, and at the current time, the measurement of the Hubble constant provides the best test of our standard cosmological model. And to tie in what we measure with the microwave background, where we're measuring at a redshift of 1100, with what we're measuring locally today, do those measurements line up? And the test of that is to measure an accurate value of the Hubble constant. So that's changed over time. When we began the Key project, the goal was to measure the Hubble constant to 10% accuracy, and that was to overcome the factor of 2. There was a debate at the time from the mid-1960s to 1990 about whether the Hubble constant was 100 or 50 kilometers per second per megaparsec. And those two values were what Sandage and Tamon and de Vaucouleurs were debating. And at the time, it was characterized as a difference between 50 and 100, but you can also see that there were many measurements made by others that fell in that gap. And the uncertainties here had been underestimated. The error bars, which were estimated to be about 10%, didn't even overlap. And in many cases, they were analyzing the same data. They were treating reddening differently. They were using different kinds of calibrators and so on. And that debate eventually was resolved as we got better and better technology with charge-coupled devices and infrared arrays, and in particular to be able to account for reddening by dust. And that just wasn't feasible before the development of CCDs. I will say that it's something that we need to be still very aware of, the difference between precision and accuracy. We sometimes have characterized this as an era of precision cosmology, and each method that we use might have very small internal scatter and be very precise. But of course, what we need is an era of accurate cosmology, and that is a very difficult task. So it's been always my view that you need more than one kind of distance indicator if you're going to overcome systematics. So Cepheids have a lot of strengths. They also have their own weaknesses. The fact that they are embedded in regions of star formation, they're young stars. They haven't had time because of peculiar motions to wander away from their locations where they formed. So they are in the dust. They're in regions of high star formation density so that the stars can be crowded or blended with other stars. And that needs to be corrected for. They also have a dependence on metallicity, the abundance in their atmospheres, which causes a change in their luminosities, and that has not been well determined, still debated in the literature. So with Cepheids alone, we will not be able to ensure that we've overcome the kinds of systematics that historically have been an issue. And now we're talking about wanting to have 1% precision, 1% accuracy to compare with the measurements that are coming out of the cosmic microwave background. So our focus in our group has been to use several methods. We've been developing a method using red giant branch stars for many years now, and a new method using a type of carbon star. And I will also say something about that. But our JWST program is a focus on all three of these methods and then applied to the type 1a supernovae. So not just relying on Cepheids alone, which has been the case in recent years. Then briefly, the Hubble Space Telescope, again, allowed us to get outside of the Earth's atmosphere and make measurements that were much higher resolution and where we could first discover Cepheids, but also where crowding and blending problems were minimized. And these were the results that we got from the key project. This is the I band at 8,800 angstroms as a function of the period in days, and that's the Leavitt law. And our measurements were based on a number of secondary methods. So again, multiple methods, which I believe strongly we need to overcome any potential systematic uncertainties. And these points in green are type 1a supernovae, which have proved to be recently what most people use when they measure the expansion rate locally, because they have a small internal dispersion and relative to other methods, and they extend the farthest. So the effects of peculiar motions, the random motions, perturbations due to the gravitational interaction of galaxies, they're a large fraction of the overall expansion rate locally, and the supernovae avoid that. As I often will point out when I am speaking to the public, this is the tick mark here, this first tick mark. All of Hubble's data, original data, fit within that first tick mark. So we are measuring a much greater volume of the universe than was accessible to Hubble. And for the key project, we obtained a value of 72 with a 10% uncertainty, and that resolved the factor of 2 discrepancy between 50 and 100 that had persisted for several decades. In the meantime, as we know, the measurements of the cosmic microwave background have improved considerably, and it's now possible to measure fluctuations in both the temperature and polarization of the background to a level of 10 to the minus 5. And the measurement of the fitting the acoustic oscillation spectrum for the fluctuations in the microwave background leads to a model which is consistent with a lambda cold dark matter model to incredible precision. I didn't put in the acoustic spectrum for the public, but leads to a value of 67 kilometers per second per megaparsec. And the results are consistent for both temperature and for polarization. And also recent measurements by the ACT Atacama Cosmology Telescope Group and the South Pole Telescope Group give very consistent results. And the precision in those measurements is at the better than 1% level. So it's 67.4 plus or minus 0.5. And that has set a very high bar for measurements of the local distance scale. So we have to account for the calibration, the absolute calibration of Cepheids or tip of the red giant branch stars. We have to account for differences in metallicity between the calibrators and stars that we're measuring in galaxies, that are more distant. And we need to ensure that there aren't systematic uncertainties in the supernova samples. And so we're moving over larger and larger volumes, and we have to constrain the uncertainties to better than 1% all along that chain. And that is a very challenging task. I'll skip this since we're not in a public audience, but I always like these SH initials. And when I talk to students, I tell them it's a message to study hard. And of course, the standard model now has dark matter accounting for most of the matter in the universe. The total amount of matter is around a third, and the dark energy composition counts for about 2/3 of the overall composition of the universe. And that is what we refer to as the standard model, an expanding universe where most of the matter is dark and most of the composition is in the form of dark energy. And the question now has arisen, is this broken? Is there a mismatch between the local and the measurements that are coming out of the CMB at a redshift of 1100? And essentially what we're doing is comparing results from the early universe and the nearby universe, and these are not matching. I was at the Sistine Chapel just a couple of weeks ago and inspired by that. So the red giants that we're using, people are more familiar with the Cepheid variables. The red giants are not as well known, but these, of course, our own sun will eventually evolve into a red giant star. Here's a plot of luminosity versus temperature, observational version of the Hertzsprung-Russell diagram. This is for a nearby galaxy in the local group. And you can see a well-resolved red giant branch here. This is the horizontal branch. And what we're looking at is the tip of the red giant branch, the TRGB. And this is the position at which the core helium flash occurs in these stars. So these stars have evolved off the main sequence. They are no longer, they've fused all the hydrogen in their cores into helium. The star had then collapsed and ends up with a degenerate helium core. And there's a hydrogen shell that surrounds the core that is powering the luminosity. And that shell is fusing more hydrogen to helium, which gets deposited on the core. And when the core exceeds a mass of about a half a solar mass, this is well understood nuclear physics, the degeneracy is broken. The temperature is about 100 million degrees at that point, and the triple alpha process can then proceed. And you break the degeneracy. There's a runaway thermal effect because of the degeneracy of the core. And very rapidly, the star then will settle down after the core helium flash onto the horizontal branch. And the net result of that observationally is that you don't have red giant branch stars above the tip. And you do have asymptotic giant branch stars. These are more massive stars, but the ratio of AGB to TRGB stars is about 1:4. So this tip observationally is well defined. So we did a study with Hubble in the halos of nearby galaxies, measuring these tip stars, which you can't see when the contrast allows you to see the disk, but we pointed Hubble in the outer regions of nearby spirals so that we could measure, and in many cases, 1,000 or 10,000 stars in these outer halo fields. So an advantage of the tip of the red giant branch method is that these red giants exist, of course, in both the disk and the halo, but we can avoid the disk altogether. Where the dust is located, the crowded high surface brightness regions where the crowding and blending effects are significant, and we don't have a large metallicity dependence. This is a fairly constant luminosity here, small dependence, which we can empirically account for. But a lot of the complications that we have with Cepheids are totally absent from the tip of the red giant branch method. And these are the fields, again, where the types of fields in the halos where we have pointed JWST. And here is another color magnitude diagram, HR diagram, showing the red giant branch, in this case, the asymptotic giant branch. And we can measure the luminosity function of the AGB and the red giant branch. And we're looking, of course, for this edge. So we have measured, we've done this with maximum likelihood fitting, but of course, to use the analogy of a cliff, the cliff doesn't know about the outer parts as a person is walking along. We're really looking for the edge. What we do is fit for the first derivative of the luminosity function. We use well-defined edge detecting techniques. We also have done maximum likelihood. They give the same result. And we do a lot of artificial star experiments where we inject stars that have the same luminosities and colors or temperatures as the red giant branch stars, inject them a few at a time so that they don't increase the crowding or blending issues, and then extract them in the same way as we do with the actual data to get a good, robust estimate of the uncertainties on the magnitudes. So it's very simple in a practical sense to do. And we don't have to worry about multiple observations to get periods and in the way that we do for Cepheids. So this was our result in 2019. I'm showing here the value of the Hubble constant as a function of year of publication. This is the value that we got for the Hubble Key project, so starting with that. And the blue points here are the value of the Hubble constant that's been obtained calibrated with Cepheids. And since the Key project, people have used type 1a supernovae, as I showed you, with the small dispersion. So the value of the Hubble constant really has remained quite constant with time based on Cepheids alone. But what has changed is that the uncertainties that are being quoted are coming down quite considerably. And the most recent publication based on the Shoes team results is a Hubble constant that has an accuracy of 1%. And the black points here are showing the results that are coming from measurements of the cosmic microwave background, beginning first with WMAP here. And you can see early on there was very good agreement with the local measurements of the Hubble constant. But as the uncertainties in the microwave background measurements came down, with Planck having many more frequencies, higher resolution, the accuracy or the precision that is being claimed by Planck is at the better than 1% level. So as we started our Hubble project with the tip of the red giant branch, we expected to either confirm the local value or the CMB value, but we in fact ended up in the middle with a value just shy of 70. So there actually are two different discrepancies here. One is the discrepancy that's being claimed between the CMB and the Cepheids, and that now is being claimed to be at a 5 sigma level, which would be beyond, I think, well established, we would be done. But there's also a discrepancy between the tip of the red giant branch and the Cepheids. And this is a different kind of discrepancy because we are measuring distances to galaxies here. The galaxies are at a single distance, and that's not telling us anything about fundamental new physics. So we need to understand the reason for the difference between the tip of the red giant branch and the Cepheids. That's telling us that there are systematics in the measurement of distances. And that's where James Webb now comes in. And for those of you who aren't as familiar with James Webb, this is a 6.5 meter telescope. Hubble's a 2.5 meter telescope. And it's optimized for the infrared. So there are 18 mirrors here. All are gold coated to be sensitive to infrared radiation. So Hubble is primarily sensitive to optical, and James Webb has been optimized for the infrared. It's not serviceable in the way that Hubble was. It's located at L2, and that's 1.5 million kilometers away from Earth. It's an Earth trailing orbit and will not be serviced. Flawless launch, which is amazing. This is a telescope that had to be deployed. All of the mirrors had to be opened. The telescope structure, the sun shield here, really phenomenal technical feat. Not just an indication of its orbit, Earth trailing orbit. And just a selection here of some of the images from JWST. Really has impacted pretty much every field in astronomy and astrophysics, and only just beginning. And the increased resolution in our case for the Cepheids and TRGB and our carbon stars is a huge step forward in terms of what we could do with Hubble. I kind of like this image. This is actually real image taken by JWST. And of course, the infrared capability allows us to do a lot better with dust. The only unfortunate thing for us right now is that we have a single wavelength with JWST, and our two other wavelengths are based on archival data from the SHOES group to allow us to get the extinction, the distance modulus as a function of inverse wavelength that allows us to fit for the reddening. So that will improve in future as we get more JWST measurements, but we still are, as is the SHOES group, confined right now to using also archival HST data. So what we planned was a simultaneous observation of these three different methods. So we have one of the NIRCam cameras in the disk that is localized to discover, to follow up the Cepheids. And then the outer disk is the JAGB carbon stars that are an intermediate age population. And then in the halo, the tip of the red giant branch stars. So we can do this all in one shot and measure the distances now to our calibrating galaxies, which have supernova observations. Type 1a supernovae have occurred in all of the galaxies that we are using, and Cepheids have been discovered in all of these. So again, the measurements allow us to make three independent estimates of the distance to the galaxy. And the galaxy, of course, is at one distance. But it allows us to understand where the systematics are potentially in each of the methods. And each of the methods will have their own uncertainties, and we need to understand at what level those are if we're going to measure the Hubble constant to 1% accuracy. Here's an HST image of one of our galaxies. This is one of the first galaxies that we measured, NGC 7250. And here it is, a JWST image. We can see many red stars turning up. The red stars, by the way, I should say, in the disk, because we're now observing at infrared wavelengths, those are the stars, the red giant branch stars and the asymptotic giant branch stars that now crowd and blend with the Cepheids. So in the optical, they're not nearly as visible. The Cepheids are relatively blue, and the red giants in the HST images are not a significant problem. But as you go to the infrared, these red giant branch and asymptotic giant branch stars are much brighter than the Cepheids, so they are contributing to scatter. This is a Cepheid in NGC 7250. This is now observed with Hubble. And this is an image of a region in a galaxy where a Cepheid was discovered at optical wavelengths. And then in the near infrared with Hubble, this is the image that is taken with HST. So the Cepheid is in here somewhere, but you can see that the background is much brighter than the Cepheid itself. And when we go to JWST, where you can see in a glance why this makes such a difference, improved resolution and sensitivity. So there's no question now that we can obtain more accurate results with, again, here's the HST image, and here's the contrast with JWST. Here are some other examples. Again, so different Cepheids, but you can see the resolution with JWST is hugely improved in terms of what we can do. As I mentioned before, we are still limited, however, with having to correct for reddening based on the archival VNI data. And that will improve in future, but it's one of the uncertainties that we have to contend with now. And as I said, we're not the only group that has to contend with that. I omitted for the public talk discussion of the carbon stars. So let me just say a few words about those before I turn to results. And I'll just mention that these are stars that are intermediate age. They are double shell burning now. So they have a carbon-oxygen degenerate core, and they're surrounded by a hydrogen burning and a helium burning shell. And it turns out that at this stage of evolution, these stars are dredging up carbon from the interior layers. When the more massive stars, they're hot, they burn the carbon before it gets to the surface. And the less massive stars, they never get to the point of being able to dredge up the carbon. So it turns out that there's a population of stars that has almost essentially an identical luminosity in the J band at 1.2 microns. And this was discovered by Nikolaev and Weinberg almost a quarter of a century ago. And they used these stars to measure the geometrical tilt of the Large Magellanic Cloud nearby. So you could imagine there might be systematic effects that could increase the dispersion in that luminosity. But they were able to measure the offset with respect to the inclination of the Large Magellanic Cloud, which agrees with what we have measured for Cepheids and other stars in the Large Magellanic Cloud, which again constrains the possible systematics. We then went and compared in a large sample of galaxies nearby the distances obtained from that method with the tip of the red giant branch, and there's extremely good agreement. And now we've extended it to JWST for our sample of 10 galaxies. And again, there's extremely good agreement. So it is appearing to be a very precise distance indicator, comparable in precision to the tip of the red giant branch and Cepheids, again, with very different systematics. So if we look at now the relative probability density distribution, this is for the Planck measurements that come in at 67.4 with this precision of 0.5. And that's what the Shoes group gets, 73 plus or minus 1. And our results at the moment are coming in at 70 kilometers per second per megaparsec. So they are in agreement at the 2 sigma level with both the Shoes measurements and Planck, but they're not indicating that the Hubble constant is as high as 73. I think at the moment, the biggest uncertainty for all of the local measurements is that we have a small sample of galaxies for which there are galaxies that are host to type 1a supernovae. Supernovae are rare. They occur only once per century in a given galaxy. And so there is a sample of roughly 40 galaxies now where Cepheids have been discovered, and there are type 1a supernovae that have been measured. We have a small fraction of that sample, so the uncertainties are statistically, we have a larger uncertainty there, but we have the 3 different methods rather than just the Cepheids alone. This will be improved as we obtain more Cepheid, TRGB, JGB calibrators with James Webb, and that's coming. Many observations have already been taken, and that will improve with time. But I think the fair thing also to say is that at the current time, there's no compelling reason to believe that we need to add additional physics to the standard model. These results are consistent with the CMB results. So I will end here with some time for questions, but only also to add that the upcoming decade is going to be an extremely exciting one in terms of observations and new facilities. We've got Giant Magellan Telescope, which we hope will be operational in the early 2030s. There's the also 30-meter telescope and the EELT, which is scheduled to be operational still, I think, at the end of this decade. We now have JWST, which is really just beginning in terms of what it can contribute to both the distance scale and many other fields. Roman, the space telescope that is going to be operational, launched in 2026, which will be an infrared survey telescope. Again, extremely important for red giant branch stars and our carbon stars. Rubin, which is now being completed in Chile, which should be operational within a year, doing large surveys, many that increase to the numbers of supernovae that will be discovered, and I hope followed up with spectroscopy. LIGO, which eventually we hope, LIGO and Virgo, which will provide a different means of measuring the local distance scale using neutron star binaries. And unfortunately, that's proved to, at the moment, the rate at which those objects are occurring is lower than anticipated. There's only been one such object that was observed in 2017, and there hasn't been another one since. But that one, for me, is, I think, really important. It will take a while to get statistics, unfortunately, that rival what we can get with the other distance indicators, but it is completely independent of the local distance scale. And so ultimately, I think that's going to be extremely important. And then, of course, the future beyond HST and JWST and larger optical telescope with ultraviolet and infrared capability in space. So I'm happy to answer questions if you have them, and I'm going to end here. So thanks very much. And I don't hear you again, sorry. Ah,
Cosa?
yes, now I hear you.
Can you hear us
Yes.
now? Okay, beautiful talk, very exciting. And I'm sure there are many comments. Rashid, you have any? And I ask Liang Li if he has any, and eventually I will ask also a question, but I don't want to do that until not to be too revolutionary.
I ask you, do you expect in the nearest 1 or 2 years that there will be, how to say, united point of view about the discrepancy between CMB data or absence of discrepancy between CMB data and optical data in the nearby universe? And do you think also that it is natural that some difference might occur? Is it natural or not for you?
So in terms of whether we will resolve the discrepancy in the next couple of years, I'm quite optimistic. I think we are already learning a lot, and we're limited simply by small numbers. And as those numbers increase, I think we're going to see how this will resolve, because we are working within the same galaxies. And as I said, there's only one distance to a galaxy. So these three different methods are offering us a way of putting a robust constraint on the uncertainties. That then there's still the issue that we're all using type 1a supernovae. And I think there are still ways in which those supernova samples could have their own systematics. And we're seeing that not at a level of the discrepancy between 67 and 73, but there are differences in the supernova samples. And so there are now measurements with spectrophotometry that improve the calibration of the supernovae, and that will happen in the next couple of years also. And then as the samples get bigger, it will be possible to really compare apples with apples, the same kind of supernovae in the host as well as the more distant sample. But I think what we're seeing, the improvement in the distances in the measurements that we can get from JWST really allows us to get to the issue of crowding and blending. Some of the more nearby galaxies have been looked at with JWST, and they don't seem to be terribly problematic. But when you go out a factor of 2 farther, you have a fixed resolution of your detector. And HST, as we've seen, didn't have high signal noise. It didn't have high resolution. So there may be systematic effects there. So we will, I think, in a couple of years, really have gotten to the bottom of that. And I am optimistic about that. In terms of whether there's a natural explanation, I think people have really spent the last decade looking for explanations, and there isn't a natural explanation that has surfaced. I think right now people are still looking at the possibility of an early dark energy component, but that would have to, you have some scalar field that would be right before recombination that would have to come in just the right way and increase the expansion rate and then disappear right before recombination. So Lambda CDM now in the Planck data, there's a 6-parameter fit, so you can trade and you can add an extra 3 parameters for the early dark energy. But there's, that is, I think, an explanation that at a fundamental physics level is not satisfactory. It's pretty arbitrary. And the constraints now are really quite tight because the rest of the peaks are so well measured. There's now also baryon acoustic oscillation measurements, which are measuring the fluctuations in the matter spectrum, so not just radiation. And there's no room to do this locally, so it appears that it would have to be sometime before recombination where it would have enough, so it won't affect what you're already constraining really well with the CMB. So I think this remains for me a really interesting question because, as I said, this is the way to probe whether or not the standard model is right. The measurement locally really does test the standard model, but I think onus is on us to show that we can make these measurements to 1% accuracy, not just precision. And I think there are a number of areas where I do have still concerns that systematics are, we haven't been able to rule out. So I don't see this at the moment as a five sigma discrepancy, and everything depends on what you take for sigma. And so if you say the metallicity dependence on Cepheids is small, and you take a small error, and if you don't allow for the scatter in the colors, which we do see in the Hubble data, which will affect the reddening, will affect your metallicity correction, and it also affects your crowding corrections. So I think we have work to do, and I'm optimistic that in the next couple of years, we will get to the bottom of this. So that's the answer to both questions. We have work to do. And that's, to say, I'm a harsh critic of this. I think historically, systematic errors have been very difficult to overcome. And when we're talking about 1%, when we're thinking about things like calibration, crowding, reddening, metallicity, et cetera, that's a real challenge. And the other thing to be said is that we're now measuring these distances that are agreeing to, in the worst case, 2.5%, in some case better than 1% for the different distance indicators. That's a huge improvement when we were talking about factors of 2 before the launch of Hubble. So we've come a long way, but getting to that last, if we want to really say this is 5 sigma, I just think we have a ways to go.
Any additional comment or question?
Thank you very much for the great talk. I heard somebody wondering whether the homogeneity and isotropy would.
No, no, I heard homogeneity and isotropy, and then I lost you.
Okay, so maybe on the region which we can probe that they might not hold true. What would be your take on that? So that this could be an additional factor for bias.
Yeah, I think it's a question of level. When we were arguing about a Hubble constant between 50 and 80 at the time of the Key project, you could say that we're living maybe in a local underdense bubble, so the expansion rate would be higher and that it wouldn't be reflecting the true overall global value. The samples of supernovae now, though, are 1,000 or so and climbing. And so those kinds of effects are really now statistically below the 1% level. If things were much bigger, we would see this would show up in the microwave background. And so, yes, this could contribute some additional noise, but we're now talking about a very small effect overall. So it's not an effect that could explain the tension. But, you know, it could add up. It could be part of the solution, but not a significant chunk of it.
You have a question?
Yes. Wendy, it was a great talk. Thank you very much. Fully understandable. Do you hear me?
Yes, I do.
Yes. And many, many thanks for this. In addition, we all know how many years you spent.
Oh, now you dropped out again. Whoops. How many years I've spent, you said.
So we are sure that you are one of the most experienced people in the world in this problem. And many thanks also to you, because you are all these last years, you were very stable in your point of view. And at the same time, you were not attacking anybody, you were just telling what is the truth of your opinion. And thank you very much. It is very impressive. And
Oh, lost you again.
thank you.
Thank you for your comment.
Thank you.
Okay, if there are no more questions, and let's thank Wendy very much. Hope next time to have her in presence.
I hope so. Thank you.